Good afternoon, friends. Today we are going to see how to draw the velocity diagram for the given mechanism. Yesterday we have seen that the velocity diagram for a slider crank chain. Today we'll see the velocity diagram for a double crank chain. Let us assume that this is the given mechanism in which you have link A, B, C, or D. This is the pairs actually. You have the link AD, which is link number 1, AB, which is link 2, and BC, which is link 3, and CD, which is link 4. Now we have to draw the velocity diagram for this mechanism. Let us assume that the crank AB is rotating with angular velocity omega. We know that when beginning with the velocity method, we first have to pinpoint the fixed point at one junction. Here point A and point D are the fixed points, hence I am junctioning them at one point. Since the link AB is rotating in a clockwise direction, that means the velocity of point B with respect to A will be perpendicular to AB and will be in the right hand side direction. So drawing that same line which is exactly parallel to the velocity of B, but this line is perpendicular to AB, and this is what velocity of B with respect to A. Now where exactly is the location of point B? To do that, to get that, first we have to calculate velocity of B with respect to A. Since we already know omega, which is the angular velocity of link AB, and that the perpendicular distance of point B from A, which is AB, hence the velocity of AB becomes omega AB into AB. So we can calculate the velocity of AB from here. Now by choosing a suitable scale, for instance, if VBA, that means the velocity of B with respect to A is 5 meters per second, is assumed to be 5 meters per second, then by choosing the scale of 1 meters per second is equal to 1 centimeter, we can locate the point B, which is exactly at 5 centimeters, but along the tangential direction to the velocity of B or perpendicular direction to the link AB. Now from the point D, we know that velocity of C will be perpendicular, but we do not know exact direction, that it will be facing right or left, but we know that it will be tangential, it will be perpendicular to the link CD from the point D. So just extend this line from the point D such that it is perpendicular to CD, and this is what, this is velocity of C with respect to D. Similarly, the velocity of C from the point point B actually, which is onto the link 3, will be perpendicular like this, right? But it is from the point B. So from point B, draw the perpendicular like that. It is clearly visible that the intersection of these two lines will be over here, which can be named as point C. Now this length over here, or this direction over here, represents velocity of C with respect to D, whereas this direction represents velocity of C with respect to B. Therefore velocity of C with respect to D is equal to length of CD, right, meters per second, and velocity of C B, that means velocity of C with respect to B, is equal to length of CB, meters per second. Here absolute velocity of C is given by VCD because point D is fixed, whereas the relative velocity of C with respect to B is given by VCB, and velocity of B with respect to A is nothing but length of AB, which we already know in meters per second. Let us assume that there is one intermediate point E onto the link BC, and we have to calculate velocity of E with respect to C, or velocity of E with respect to D, if we have to calculate that. So to do that, we have seen in the last lecture that the relation BE upon BC is equal to BE upon BC, where B, E and C are points on the same link, right? Therefore BE is equal to BC into capital BE divided by capital BC. Hence we can easily get the point E, which is on the line BC and somewhere at a distance E from at the distance BE from the B here. Hence the absolute velocity of point E is obtained from the fixed point, which is A. This will be velocity of E with respect to D, which is a absolute velocity.